Hello and welcome back. In this video, I want to talk about potential energy and conservation of energy. But before we talk about conservation of energy, I want to talk about what types of forces conserve energy. So in the previous two videos, we found something that was pretty extraordinary. We found that the work that's done by gravity is always equal to mg times the initial height minus the final height. So for example, if we have, say, a person who's standing up here and they drop a stone, the stone's initially at some initial height h0, and then it lands down here at some final height h final. The work that's done by gravity was just the force due to gravity, which is mg times the initial height minus its final height. Another way we could write this is it's minus mg delta h. The minus sign comes because, remember, delta h is h final minus h initial, but the work done by gravity is h initial minus h final. So what this means was that the work that's done by gravity only depends on the initial and final height. It doesn't depend on the path that's taken. So, for example, we saw this example where a student takes a stone and he throws it off of a building. And we found that the work that was done by gravity doesn't depend on how the stone is thrown. So if it's thrown at an angle, or if it's thrown horizontally or vertically upwards or downwards, the work that's done by gravity is always minus mg delta h. It doesn't depend on the path that's taken by the stone. And it turns out that this is not a really unique thing. There are a lot of forces like this. So whenever the work that's done by a force only depends on the initial and final positions, we call this a conservative force. So a conservative force, the work that's done by a conservative force, does not depend on the path that's taken. It only depends on the initial and final positions. Now, forces that aren't conservative are called non-conservative forces. So I just want to look at a couple of examples of these types of forces. So conservative forces, for example, the gravitational force is obviously a conservative force. It turns out the universal gravitational force is also conservative. So the force that is exerted on the moon or a satellite or something like that is a conservative force. Hooke's law, spring force, is a conservative force. The Coulomb force, which we haven't talked about yet, that's the force between charged particles, is also a conservative force. Examples of non-conservative forces are things like friction, drag, tension, and pressure. You'll notice that some of these things, like friction and drag, these are things that tend to slow objects down. These are things that aren't going to conserve energy. So that's where these terms come from. Conservative forces will tend to conserve energy. Non-conservative forces will not conserve energy. So it turns out for any conservative force, we can always write the work that's done by the conservative force as being equal to some function of the initial position minus a function of its final position, right? If it only depends on the initial and final positions, we should be able to write the work that's done by the object like this. So for example, the work that's done by gravity is equal to mg times the initial height minus mg times the final height. So this is a function of the initial position minus a function of the final position. So for example, in the case of gravity, our function of height is equal to mg times the height. And whenever we write the work that's done by a conservative force like this, that function is called the potential energy. So what this means is that the work that's done by a conservative force is the initial potential energy minus the final potential energy. So the work that's done by a conservative force is minus the change in the potential energy. So what this means is that as work is being done by a conservative force, the potential for that force to do work is decreasing. So for example, when you drop an object, as the object falls, and as gravity does work on that object, the potential for gravity to do work on the object decreases because the height of the object is decreasing. So there's less potential now for gravity to do additional work because the object is lower, it's closer to the ground. So that's why there's this negative sign there. So let's go ahead and look at a simple example. This example says, a 10 kilogram box slides down a 10 meter frictionless ramp which forms a 30-degree angle with respect to the horizontal. The only forces acting on the box are gravity and the normal force. This problem asks us to verify that we get the same value for the work using the potential energy formula as we get using the formula for work. So let me go ahead and open up a blank screen. So what we were given is that the mass of the box is equal to 10 kilograms. And it's going to slide down the ramp 10 meters. And the angle of the ramp is 30 degrees. So let me go ahead and draw a picture of what we have here. So we have this 30-degree ramp. And we have this box on the ramp. And the box is going to slide 10 meters down the ramp. So it's going to go this direction 10 meters. So let's first use the formula for the potential energy due to gravity. So the work that's done by gravity should be minus the change in its potential energy. And the potential energy for gravity, remember this is mgh. So we have minus mgh final minus mgh initial. So if I distribute the minus sign, that's mgh initial minus h final. So what I need to do is calculate the initial height and the final height of the box. So if we look at this, if the box is going to slide 10 meters down the ramp, then the initial height of the box, so this height right here, if this hypotenuse is 10 meters, that's how far I'm going to travel down the ramp, then the change in my height, that's this thing right here, right? This is my initial height right here. This is equal to, so it's opposite the angle 30 degrees. So this is 10 meters times sine of 30 degrees. So h initial is 10 meters times sine of 30 degrees. So I hope that makes sense, right? Let me just kind of draw a little picture of what's going on here. So my displacement looks like this. This is my delta r. And I'm trying to find how far I move in this vertical direction. So I'm looking for this, right? So if delta r points down, then delta h points down and has a length of 10 meters. That's this thing right here. The magnitude of this is 10 meters times sine of 30 degrees, because this angle right here is 30 degrees. So we see the work that's done by gravity is mg times 10 meters times sine of 30 degrees. Right, the initial height is 10 meters times sine of 30 degrees. The final height down here is 0. So the final height is 0. So if I plug all this into a calculator, let's see, oh, I don't know what this is. I should have typed this into a calculator before starting these notes. But I want to verify that this formula is going to be the same thing as if I calculate the work going down the ramp. So the work going down the ramp, one way we could calculate this is it's the force that's due to gravity times the component of my displacement that's parallel to the gravitational force. So that's mg, and again, looking at this, the component of my displacement is parallel to the gravitational force. The gravitational force points down, right? So the component of my displacement that's parallel to this is this component of the displacement right here, so delta h. So we see it's going to be mg delta h, and delta h we said was 10 meters times sine of theta, or sine of 30 degrees. So either way we calculate this, we get the same thing. So it turns out that in the absence of non-conservative forces, the work-energy theorem reduces to conservation of energy. So the way we can see this is the work-energy theorem says the sum of the work that's done by all the forces is equal to the change in the kinetic energy. Now, if all of my forces are conservative, so I'm summing up a whole bunch of conservative forces, well, we know I can write the conservative force as minus the change in the potential energy that's associated with each one of those conservative forces. So the force due to gravity has some potential energy, and the work that's done by gravity is minus a change in the potential energy due to gravity. And I could do that for every single force that's conservative. this has to equal the change in kinetic energy according to the WorkEnergy Theorem. So let me go ahead and write this out. So this is saying the sum of, so minus the change in the potential energy. So minus the final potential energy minus the initial potential energy. Right, remember, delta is always final minus initial. Is equal to the final kinetic energy minus the initial kinetic energy. So if I put all the initials on one side and the finals on the other, let me go ahead and distribute the minus sign actually. So if I distribute the minus sign, then this thing will be negative and this will be positive. So if I move all the initial stuff to this side, the final stuff to the right side, so here I'm going to add the kinetic energy over here, so I have the initial kinetic energy plus the sum of all my potential energies is equal to my final kinetic energy plus the sum of all of my final potential energies. And if I call the kinetic energy plus the sum of all of my potential energies the total energy, I see that the initial total energy is equal to the final total energy. So energy is conserved. The total initial energy is equal to the total final energy as long as all of our forces are conservative. Or if we have a non-conservative force, it just doesn't do any work. So let's go ahead and look at a couple of examples. The first example says, a ball is launched down a 3-meter high frictionless ramp with an initial velocity v0. At the end of the ramp there is a curve which launches the ball vertically upwards. The ball reaches a maximum height of 4 meters. Assuming the ball slides without rolling, what was the initial velocity of the ball? So the reason I say it slides without rolling, remember I talked about this briefly before. When an object rolls, there's actually a kinetic energy that's associated with that rolling motion. Okay, so a lot of times when we talk about objects like balls and stuff like that, we'll always be assuming that they're not rolling. So this is a picture of what we have. It's initially moving. It's going to come down the ramp. It's going to come up here, and then it's going to be launched into the air. So it's initially starting out 3 meters above the ground, and it's going to end up here 4 meters above the ground. So because all of these forces are conserved, right? The only force that's acting on the ball during all of this is gravity and the normal force of the ramp. And the normal force of the ramp doesn't do any work on the ball because it's always perpendicular to the direction the ball is moving. And gravity, we know, is a conservative force. So because all of the forces acting on the ball are conservative, we can see that the final energy is equal to the initial energy. So the final energy, if I wind up here, so this is my final position, and this is my initial. So in my final position, I'm at the maximum height, and the ball is launched vertically upwards. So at the final position, we have that the final velocity is 0 meters per second, right? Because I'm going to come to rest when I reach the maximum. So the final kinetic energy is 0 joules. So we don't have to worry about that. So the only thing I have for the final energy is the final potential energy due to gravity. And this has to equal my initial energy. So initially, I'm up here at the top of the ramp and I'm moving. So I have both gravitational potential energy and kinetic energy. So the total energy that I initially have is the initial gravitational potential energy plus the initial kinetic energy, 1/2 m v0 squared. And what I'm asked to solve for is this v0. So let's go ahead and plug in the formula for gravitational potential energy. So this is mgh final is equal to mgh initial plus 1/2 m v0 squared. We can see the masses cancel out. If I'm solving for v0, so I want to move this over to the other side, so I have 1/2 v0 squared is equal to gh final minus gh initial, so I just subtracted this over to there. I'm going to multiply by 2 and take a square root, so I get v0 is equal to 2g h final minus h initial, and then I've got to square root the whole thing to solve for v naught. So here I'm just doing some algebra to solve for v naught. And if I plug all this into a calculator, I'll see that this is equal to 4.43 meters per second. So that was how fast this ball has to be traveling up here at the top of the ramp, so that when it comes down here and then gets launched into the air, it'll reach a final height of 4 meters. So let's go ahead and look at one more example. This example says a roller coaster sits at the top of a frictionless hill and has an initial height h naught. At the bottom of the hill is a loop that has a radius r. If the roller coaster starts from rest at the top of the hill, how high does the hill need to be in terms of this radius of the loop so that the roller coaster will be able to make it through the loop? So let's see, do I have a... Let me go ahead and open up a blank screen here. So remember that when we have circular motion in a vertical plane like this, so what we have, right, we have this hill here, it's going to come down, it's going to go through this loop. So if I draw the free body diagram of the coaster right here at the top of the loop, there are two forces that are acting on the roller coaster. Let me go ahead and draw a little bit bigger picture of what's going on here. So this is the top of the loop here, drawing a real big picture of this. I've got this coaster right here at the top. And there are two forces that are acting on this. There's the force due to gravity that pulls down on the roller coaster, and then there's the normal force that this track is going to push down on the coaster. Okay? Oops, the normal force. Now, if the coaster just barely makes it through the loop, then it kind of like loses contact with the track, just right there momentarily when it reaches the top of the loop. Right? So at the very top of the loop, that normal force that's being exerted will be 0. Okay? So the force that is being exerted on the coaster, if it has just enough speed to make it through the loop, is just the force due to gravity. And this force is pointing inwards towards the center of its circular path, right? So when it goes around a loop, it's traveling in a circular path. So we know the acceleration is going to be equal to mv squared, or v squared over r. So what this means is that because my gravitational force points inwards towards the center of the circular path, and I know my acceleration has to point inwards towards the center of the circular path, and the acceleration has to be v squared over r, I see that the force due to gravity has to equal m times the centripetal acceleration, which is mv squared over r. And the force due to gravity is, of course, mg. So what this means is that my speed that I have to be traveling at the top of this loop is related to the gravitational force. So at the top of the loop, the velocity I have has to be equal to the square root of g times r. So this is how fast I have to be traveling when I'm at the top of the loop. So I'm going to call this point up here at the top of this hill the initial position. And I'm going to call this point down here my final position. And using conservation of energy, I can figure out how high this hill has to be. So we'll call this h initial. Right? Now I know how fast I have to be moving here. I know how high off of the ground I am here. Right? If this loop has a radius of r, then at the top of the loop, I'm 2 times the radius of the loop up above the ground. So using conservation of energy, we have the initial energy has to equal the final energy. So initially, I said I'm starting from rest, so my kinetic energy is 0, so my initial energy is just the initial gravitational energy. The final energy is the final gravitational energy plus the kinetic energy at the top of the loop, because we said I have to be moving when I reach the top of the loop. So now I want to plug in for the formula for kinetic energy and plug in for the formula for gravitational potential energy. So this is mg h naught is equal to mg, and actually, right, so we think about this, right? The radius is r, so up here I'm 2 times the radius above the ground, so this is 2r is the height here, plus 1/2 mv squared. But at the top of the loop, my velocity is the square root of g times r. So the square of my velocity when I'm at the top of this loop is gr. So if we look at this, we see mg appears in all three of these terms. So we can go ahead and cancel out m times g. So what we see is the initial height is equal to 2r plus 1/2 r. So the initial height of the coaster has to be 5/2 times the radius. So in other words, the coaster has to initially be 1/2 of a radius above this point, this top of the loop. So at that point, I think I'd like to end this video. And in the next video, I want to talk about how non-conservative forces change the energy of a system.